After studying this module, you shall be able to know about symmetry and antisymmetric orbitals, representation using px, py, pz orbital as the basis, see the effect of E, sigma, C2 and I operation on px, py, pz orbital. See the effect of symmetry operation of C2b point group on px, py, pz orbital. Know the effect of various symmetry operation on unit vectors lying along Cartesian coordinates. Know the generation of 3:3 matrix for each of the operation using xyz unit vector as the basis. We have learned about matrix algebra in very brief. The matrices behave very similar to symmetry operation of the point group. These combine in similar fashion. How to quantify the effect of symmetry operation so that one can apply group theory more effectively and in systematic manner. This can be achieved if we can represent each and every symmetry operation of the point group by a matrix generated by taking Cartesian coordinates, orbitals, base vector, wave functions, etc. as the basis for the representation. Effect of symmetry operation on these bases provide matrices corresponding to these symmetry operations. These matrices for each and every operation of the point group form a homomorphic group. These matrices behave very similar to symmetry operation of the point group. This means the effect of symmetry operation parallels the effect of matrices corresponding to each and every symmetry operation generated by taking certain bases on a particular point group of the object. This means the effect of symmetry operation parallels the effect of matrix corresponding to each symmetry operations. Now let us discuss symmetric and antisymmetric orbitals and their representation. Let us take px orbital and perform various symmetry operations and see the effect of these symmetry operations, and let us quantify these effects in terms of mathematics. The various symmetry operations and their effects are shown as. Now, identity operation E. According to E operation, we are doing nothing on any of these orbitals. Let us take px orbital as I have shown. Let us take these px orbitals. This is y-axis, this is z-axis, and this is my x-axis in which the px orbital is lying. And we perform now various operations on this E. First, let us perform E operation. E operation means I am doing nothing on this molecule. That is, E operated on px gives me px. That is, px goes to px. And we can say that E has +1 effect on this px orbital. Or we can write down this equation as E px goes to px is equal to, within bracket, +1 px. That is, when the orbital does not change by the symmetry operation, we give it as the +1 effect. These are shown into the, that is, px remains same. If there is no change, the effect is written as +1 effect of this symmetry operation. Now let us take C2 operation and perform on this about x, y, z axis. These various operations are shown into this. That is, if I take this is my px orbital, I perform a C2 operation about this axis, that is x axis. If I go on rotating like this, the positive lobe remains positive, negative lobe remains negative. So this is called +1 effect. That is, this does not change. Now what happens if I take C2y operation? This is my C2x operation and C2z is this. Let us perform these two operations as shown into this result. If I take C2y and perform, it will go like this. Positive lobe goes into the negative lobes and negative lobe goes into the positive. So this is called -2 effect. Similarly, if I take z-axis and perform, this is my px orbital, and perform C2 operation on this, what do you see? The positive lobe goes into the negative lobes and negative lobes goes into the positive, so it is -1 effect. These are shown into, that is how this changes. -1 effect means that px orbital is anti-symmetric with respect to that symmetry operation. Here it is C2y and C2z operations. Now what happens if I take sigma yz operation on px orbital? Let me take, this is px orbital and this is sigma yz orbital. If I do like this, this positive lobe will go to the negative, negative will go into the positive. That is, this mirror image is reversed. So this will give us the minus effect. Now what happens if I take sigma xz? Sigma xz, it means positive lobe remains positive, negative lobe remains negative. So the sigma xz on px gives me the positive and sigma yz gives me the negative effect. The yz is shown into the, that is, it is reversed. Now what happens, as I have shown you about the xz, it is shown into this, it remains unchanged. So we have seen here now how yz, how xz, how C2 operation they change the px orbital. Thus px is orbital symmetric with the sigma xz. Now let us see what is the effect of inversion operation. Inversion operation means I am taking this px orbital and I will reflect through this point. Now if I do this, this and this, they will be interchanged. Finally after I operation, it will go like this. That is, it gives me the -1 effect as it is shown into the slide. That is, you will get -1 effect when I performed I on px orbital. Now here +1 and -1 represent symmetric and anti-symmetric with respect to a particular symmetry operation. Now I can write down all these effects of all symmetry operation on px orbital in a table form. That is, E gives me +1, C2y gives me -1, C2z gives me -1, sigma yz gives me -1, sigma xz gives me +1, and I gives -1, and C2x gives me +1. So here I have seen the effect of various symmetry operation on pxy orbital, and I have quantified these in terms of +1, -1, etc. Thus, by taking +-1 as the effect of symmetry operation on the px orbital, we get a representation for E, C2, sigma xz, sigma yz, I using px orbital as the basis. Similarly, we get the effect of this symmetry operation on py orbital and the results are shown. That is, we can carry out similarly the effect of various symmetry operation on py orbital. Let me take, this is my py orbital over here and this is my z-axis and this is my now x-axis, and this is my y-axis. You perform the operation as we have done in the px orbital, and the results are and all these effects of these can be put down in the tabular form over here. That is, E gives me plus 1 effect, C2x gives me minus 1, C2z gives me minus 1, sigma yz gives me plus 1, sigma xz gives me minus 1, and I gives me minus 1. That is, I have complete like this. Now what happens if I go for the effect of various symmetry orbital on pz orbital? And pz orbitals means I take this orbital in this manner. This is my x-axis, this is my y-axis, this is my z-axis. I take it this in this direction. Now pz orbital and sigma xy is shown into this, and you can perform the symmetry operation and see the result as these are tabulated below. Pz, E does not do anything, so plus 1 effect. C2z, that is I am carrying out this operation on this. C2x, C2y, C2z, sigma xy, sigma xz, and I, all these are shown into this. The effect of various symmetry operations on pz orbital is summarized in this, are shown into the table in this over here, and these are E gives plus 1, C2z gives plus 1, C2x minus 1, C2y minus 1, sigma yz plus 1, like this it is shown. These types of representation in terms of plus minus 1 using px, py, pz orbitals as the basis are known as the non-degenerate representation. That is only the plus 1s result. Now what happens if we take representation of C2v point group using px, py, pz orbital on the oxygen atom? In C2v point group, there are E, C2, sigma xz and sigma yz symmetry operations. These px, py orbitals on oxygen atom at one place, and we can now summarize the effect of various operation of C2v point group. E does not change any of these, C2 thus it changes, like this sigma xz and yz we can found, and all these effects of various symmetry operation on px, py, pz orbitals are shown into the a form of table below. That is, on in the first column we are having px, py, pz orbital. Second column gives the effect of E on these. Third column gives effect of C2. Fourth column gives effect of xyz, and fifth column gives effect of yz. Thus the effect of symmetry operation E, C2, sigma xz and sigma yz of C2v point group on px, py, pz orbitals has been quantified in terms of only plus minus 1. Then we go to another point, unit vector along Cartesian coordinates as the basis for representation. Let us take a set of unit vector represented by small x, small y, small z lying along x, y and z axis with small arrows which are lying on this. Now let us see what is the effect of E, C2x, C2y, C2z, sigma xz, sigma yz, sigma xy and I on these unit vector xyz lying along Cartesian coordinates. First let us see effect of E on unit vectors. xyz, this is corresponding as shown over here. E within square bracket xyz gives me within square bracket x dash, y dash and z dash. That is x goes to x dash, y goes to y dash, z goes to z dash. That is E operation is shown in this figure. That is, it does not change. Or we can say in equation form, x goes to x dash, which is nothing equal to plus 1x. Second, y goes to y dash, which is nothing equal to plus 1y. Z goes to z dash, which is nothing but plus z. Since x, y, z are orthogonal to each other, these do not contribute to other coordinates on performing symmetry operation. We can write down these equations for operation E as E is equal E operated on x gives me x dash, or in equation form plus 1x plus 0y plus 0z. Second equation, E operated on y gives me y dash, which is equal to 0x plus 1y plus 0z. E operated on z gives me z dash, which is nothing but 0x, 0y and plus z. In matrix form, the effect of E on x, y, z unit vectors can be written as E is equal to a matrix 1 0 0 0 1 0 0 0 1, or we can represent the whole process in terms of matrices. That is, E operates on x, y, z gives me x dash, y dash, z dash, or E of the matrix for E 1 1 1 0 0 0 1 0 0 0 1 operated on x, y, z gives me x dash, y dash, z dash. So we get a 3:3 matrix for operation E, which is nothing but 1 0 0 0 1 0 0 0 1. So this is corresponding to E operation. Now effect of C2x on unit vector xyz. This is represented, that is, after performing this operation, what happens to these various unit vectors. That is, x, we are getting x dash is equal to minus x, and the equation can be written as minus x 0y 0z. Y dash is equal to minus y, and the equation is 0x minus y plus 0z. Z dash is equal to z equal to 0x 0y and plus 1. So x dash, y dash, z dash is nothing but matrix corresponding to the C2, C2x and xyz. Corresponding to C2xz is minus 1 0 0 0 minus 1 0 0 0 plus 1. Thus the matrix corresponding to C2x on unit vector is written as minus 1 0 0 0 minus 1 0 0 0 1. Now let us see the effect of sigma xz on unit vector xyz. This is represented as shown over here, that is sigma xz operated on this, we get xz y dash z dash, and this effect is shown into the, and the corresponding equations for this are x dash is equal to plus 1x plus 0y plus 0 dash, y dash is equal to 0x minus 1y minus y plus 0z. Z dash is equal to 0x plus 0y plus 1z. And in matrix form, this can be written as 1 0 0 0 minus 1 0 0 0 1. Effect of sigma yz operation on xyz unit vectors. It can be written as sigma yz operated on xyz gives me x dash, y dash and z, and in diagram these effects are shown. And in matrix form, the three equations are x dash is equal to minus x, 0y plus 0z, y dash is equal to 0x plus 1y plus 0z, z dash is equal to 0x plus 0y plus 1z. So, in matrix form, the matrix corresponding to sigma yz is minus 1 0 0 0 1 0 0 0 1. Now, let us see the effect of inversion operation on xyz unit vector. It can be written again, I operated on xyz is equal to x dash, y dash, z dash, and these effects are shown into the over here. And in equation form, these can be written as x dash is equal to minus 1x 0y plus 0 dash, y dash is equal to 0x minus 1y plus 0z, z dash is equal to 0x 0y minus z. So in matrix form, the matrix for corresponding to I is minus 1 0 0 0 minus 1 0 0 0 minus 1. Sigma xy operation on xyz unit vectors can be written as, again, sigma xy operated on xyz gives me x dash, y dash, z dash, and the effects of sigma xy on these unit vectors. And in equation form, I can write down x dash is equal to plus 1x plus 0y plus 0z, y dash is equal to 0x plus 1y plus 0z, z dash is equal to 0x plus 0y minus z. Or in matrix form, the matrix for sigma xy can be written as 1 0 0 0 1 0 0 0 minus 1. We have seen that xyz unit vector transform into plus minus 1 only. These remains same or their directions are changed. In all these cases, we get 3:3 sized matrices for each and every symmetry operation. Now, in this over module, we have seen what are symmetric and antisymmetric orbitals, and these have been defined and explained with the help of the models. Effect of various symmetry operations on px, py, pz orbitals have been studied and explained with the help of the sketches. That is, we have taken E, C2, sigma xz, sigma yz, C2x, C2y, C2z, I, etc. operation. Mathematical effects of symmetry operations defined. Effect of symmetry operations of C2V point group on px, py, pz orbitals summarized in table. Effects of various symmetry operations on unit vectors x, y, z lying along Cartesian coordinates x, y and z have been investigated in details with the help of the sketches and models, and that is, we get in all the cases a 3:3 matrix developed corresponding to each and every symmetry by seeing the effect of symmetry operation on unit vectors. That is, we have developed 3:3 matrices for E, C2, C2x, C2y, C2z, I, sigma xz, sigma yz, and sigma xy. So, in this module, we have seen that is how we can get a quantitative way of representation of the symmetry properties.